Thanks, Arnaud, for the reminder. Okay, well, and then the homework that's due on Tuesday of next week is, I mean, okay, so I consider the homework, that homework 1 is about, you know, a replicated simulation experiment and, you know, correctly versus incorrectly specified models, and about cross-validation. Homework 2 that's due next week is about sort of similar concepts, but using a hierarchical model. So essentially, how do you get inference wrong, even if you have the model specified correctly in terms of the mean, but you have it incorrectly specified in terms of the variance of the process. So you misspecify some part of the hierarchical structure. What effect does that have on your subgroup inference? And then today, well, this week we're going to start looking at time series models. I think I was telling Abby that, you know, in my mind, the week 1 and 2 has the most, you know, a lot of statistical background material. Weeks 3 and 4 maybe slow down a little bit in terms of content. I mean, they're basically looking at sort of simple time series models. And then week 5 and 6, it ramps up again a little bit in terms of, you know, expanding this to spatial context. Okay, so as I always do, the first bits are all about review. So how about you know, we talked about how you can take a joint likelihood and factor it into, you know, a marginal and then a series of conditional probability distributions. Anybody have any more thoughts about examples, like real world examples where you might factor a joint probability into smaller conditional probabilities?
Would you use it if you have like a bunch of samples at multiple sites at a time?
Yeah.
Like if you have like a survey design and you have lots of years.
Yeah. So sometimes, like, you could have 100 observations on a 10 by 10 grid, and a lot of the spatial models we'll do later kind of factor that into, you know, the marginal probability of one datum, and then the conditional probability of the next datum given the first one, and so forth. You know, and then the third one given the first and the second. And so that's one way that you can generate what's called a conditionally autoregressive model. Any other stuff come to mind? Like, I'm sorry, it is Carlton or Charlton? Sorry, yeah. Charlton, you were talking about your project of interpolating population size between different censuses. Is there any, like, if you?
I think similarly, like, we don't necessarily interpolate, but like getting the population at the next time point conditional on the previous census.
Yeah, right. So a lot of times we do predictions. So on Thursday we'll talk about how to do predictive intervals from the Kalman filter and from the state space model, and we'll do that by taking the conditional probability of future unmeasured events given our estimate of the state. Who here was at the talk on Friday at QuantSim? There are a few of you guys, right? So that was an occupancy model. So what were the kind of conditional, you know, marginal and conditional probabilities that Robbie was looking at?
You needed the probability of detection, and then probability of observing an individual, and the probability of occupancy. And then from those two, you get the probability of observing an individual, given the probability of detection and the probability of occupancy.
Totally. Yeah, exactly. So he has a bunch of data about times when, I mean, he has a complicated, this like multi-level occupancy model, or, you know, multi-time scale occupancy model. But in the simple concept is you could have, you know, a site that you observe of, in his case, a Wolverine, right?
Mhm.
In, you know, year 2000 and 2001, not 2002 and 3, and then again in 2004. And so you can factor that, the probability of those 3 data into a series of conditional probabilities, which is like, oh, what's the probability that you missed it even though it was occupied in 2002? What was the probability that it became unoccupied in 2002, given that you know it was occupied the year before, and so forth. So that's how we do the occupancy model. And then we'll, you know, today we'll be talking about how to factor, how to break up, you know, time series and increments in a filter. Okay, so, you know, the next piece of review was, you know, about introducing these sort of latent variables, epsilon. So if you want to calculate the probability of some data given some parameters, you know, which is equivalent, you know, proportional to the likelihood of the parameters given the data. Sometimes you can do it by introducing latent variables or augmented data or random effects. And then take the integral across those random effects to get back to the probability that you need. And we talked, I think, about how that integral is sort of essentially like a weighted average across a bunch of unobservable things. That weighted average should be sort of intuitive based on that's how we do a lot of predictions of future events, given unknowable future possibilities. And we went through some of the definitions that I'll be using. So, did the Cressy article talk about exchangeability? I forget what that paper covers.
I don't think too much.
Yeah.
Let me look.
Yeah, who, I mean, I didn't really stress the readings, but did anybody, who actually did the reading of the Cressy one? That's sort of a fun one in case anybody's gonna do any particular reading. Well, I didn't stress it, so I'm not, you know, I don't really care. But yeah, I mean, well, we've talked about these a lot. Okay, so anybody wanna hazard sort of a personal definition of a state space model?
Include multiple sources of error in your model.
Yeah, which is, I mean, I'm sort of a dangerous person to learn this from, I guess, because I sort of think, I mean, there's a whole history of the evolution of state space models that I haven't gone back and read. And so that's also sort of how I define it, is like something where you've got process errors and measured errors. The issue, of course, is that ends up just being kind of like any mixed effects model. So is there any sense of like when you would call them, what mixed effects or hierarchical models you call state space and which ones you wouldn't?
Generally where the latent process is some sort of time series.
Yeah, I think that's.
Sort of more, where with Markovian dependence typically.
Totally, exactly. So, and what does that Markovian dependence mean?
The current state is conditionally independent of past states given some finite subset of the past state, typically the previous state.
Yeah, exactly. So, like.
Not quite.
What's that?
That wasn't super clear for everybody.
Okay.
I can try again.
Yeah.
So your current state, let's see, how do you say this?
I have.
You know everything about the current state that you can, generally given the one previous state, and states before that previous state don't tell you anything new about the current state.
Right.
Yeah.
So when I was learning about state space models, the general idea was there's like some initial potentially unknown condition. And then the current condition depends on the initial condition. and there's some likelihood that's dependent on the current condition.
Yeah, exactly. So that's sort of so you can build the model that way, and then the Markov assumption is that it's dependent. The state in time t is, the way you described it, it sounded like the state in time t could be dependent on t minus 1 and dependent on t minus 2 and dependent on time t minus 3 all the way back to the initial state.
Mhm.
Whereas the Markov assumption is specifically that it's only dependent on the one right before it or the two right before it or so forth. So it's sort of a way of restricting that dependence structure. And what we'll want to get to by the end of the day, and so remind me if we don't make it clear, is that has to do with separability. So we started talking about separability at the end of last class. I was having trouble finding the plot to show the Hessian matrix. But does anybody remember what I started saying about separability?
Is it the joint negative log likelihoods for the random effects were independent of each other?
Conditionally independent, exactly. So one way to think about it is, and conditionally independent is the same term that John used, and it's hard for people to know intuitively what conditionally independent means. And so there's a bunch of different ways to describe it, and I'll just take one tack now, and I'm sure by randomization I'll end up explaining this differently in future classes. Does anybody know the difference between a correlation and a partial correlation? Has anybody seen the term partial correlation? Like, if you've got a covariance matrix between a set of variables that's, two variables would be independent if they have no covariance. But partial correlation is the inverse of that covariance matrix and then rescaled to a correlation. And partial covariance is saying that if the partial correlation of the inverse of your covariance is 0, it means that two variables are independent, conditional on other variables in the model. And so that inverse covariance matrix is equivalent to another matrix we were talking about last time, the Hessian matrix. And so if you take the Hessian matrix of your random effects, you take the log likelihood and get the matrix of second derivatives. If the matrix of second derivatives is 0 anywhere between random effect 1 and random effect 2, that means that those two random effects are conditionally independent. And that means that, where was I going with that in the first place? It means that those two are independent of each other, conditional on the value of other random effects. So we'll see that at the end, and I'll explain it differently once we see it. But okay, so a state space model, we've got measurements of some process, and those measurements I'll call y sub t, and we want to use that to reconstruct the unobserved state x sub t in every year. Why would we want to use a state space model like this?
You're missing data or,
Yeah, so interpolating between observations if you're missing some. We started talking
We have
about,
multiple random effects.
what's that?
We have multiple random, like process error and
Totally.
estimation error.
Yeah, exactly. So factoring the variance, we've got some total variance in the data set, and we want to attribute some of that variance to sort of process the variance in the process versus variance in the measurement. Okay, and you can just improve your predictions of the unobserved state by sort of shrinking observations towards observations before and after it. So this is sort of the Borel's paradox, or the Stein's paradox sort of claim that we can shrink observations towards one another and get a better prediction. So So this is a first order Markov or a first order autoregressive state space model. Well, no. Yeah, okay. It's just a first order. It's not autoregressive, I guess, it's just a random walk, but it's first order Markov. So does anybody, John, you wanna, are you willing to say why this is first order and not higher order?
Yeah, so your sort of latent state is your x variable, which evolves in time, and the basic idea is if you know x of t, then you know everything you know about x of t plus 1 is given by x of t. Knowing x of t minus 1 doesn't tell you anything new about x of t plus 1 if you know x of t.
Exactly. So, so x of t plus 1 is conditionally independent of x of t minus 1, conditional on the value of x of t, which is another way of saying what John said, which is that all of the information about x of t plus 1 is contained in, all of the information from x of t minus 1 is contained in the value in x of t for informing x of t plus 1. That was the worst way of saying it. We started, but how many parameters are in this model? Three parameters, two variances in the alpha, and how many random effects are in this model? How many?
One.
Yeah, I mean, so it's sort of hard to answer because people mean different things. So there's either there's a vector of random effects x, or there's the number of coefficients in that random effect is the number of years that we're modeling. Yeah. So, okay, so really all I want to do today is just show how to fit this model with a couple different approaches. So if we're handed a data set that looks like this, we could wonder what's happening, past the last observation, so this could be 100 days looking at the location along a coastline of a Chinook salmon that we tagged, that was released at location 3 along the coastline. This could look like, we're really good at looking at curves and speculating about what it could be. So maybe we could, this might look to us like some population that went up to a carrying capacity and then was stationary up there. Or the number of infections per 1,000 individuals that increased and then stabilized. And the different things we want to do, like for instance, we could want to ask, what's the best prediction of the unobserved state times 80, and how best can we shrink it down towards observations near it. And so the different things that I see people doing are linear models, Loess smoothers, a GAM, or a Kalman filter, which is this. So I didn't actually put it in the slide. Does anybody know sort of the definition of a Kalman filter, or how a Kalman filter differs from a state space model?
Kalman filter is a specific state space model that assumes linear evolutions and Gaussian errors.
Totally. Yeah. Yeah. So it's the subset that's sort of linear and normally distributed, a normal distribution in the evolution of the state over time. Evolution of the state over time is normal, and the observation process is normal. In this case, it's log normal, but you can just log scale to y. Why? Any guesses why it has a special name?
Because it's
older than
Yeah.
state space C.
Yeah, so, yeah, I don't know too much about it, but, Coleman, I think was an engineer, or did engineering applications, and he was one of the many people that came up, with concepts that then got folded into kind of hierarchical modeling in general. And in this case, you can, because it's a normal model, you can basically solve it analytically on the normal distribution, just like least squares allows you to do a normally distributed regression, you can do this normally distributed hierarchical model analytically. And I'm not gonna go, I've never actually coded one up by hand, otherwise I'd probably just put it in here. But. So okay, so here's the linear model fit to these data. What other problems do you see with this?
Way overestimates the lower end of the x-axis.
Yeah, so it looks like there's sort of like, it's doing particularly badly on the ends.
They approximate what the data looks like.
Yeah, it doesn't, I'm actually not sure why. Maybe this is just plus and minus one standard error because it looks like most of the data are outside this interval. We can look at the code in a second, I remember what I plotted here. I mean, it seems like it does a really horrible job of, the guess is that it probably does a really bad job of extrapolating. Like, the trend is systematically wrong on both sides. Yeah, okay, so I don't get to look at that. So a Loess smoother, what's, anybody remember what Loess stands for? I actually don't. Hoping somebody does.
Local something.
Local something, yeah. I'm assuming sum of squares, I don't know, yeah, local something. Yeah, so this one at least does a better job of capturing variability. Any thoughts about why this might not be a very satisfactory model?
There's some tuning parameters in there that you could get some very different behavior that it might follow better, but
Yeah,
you know what's overfitting and what's not.
totally. So I just fit a canned package, canned function Loess and R. I have no idea how it generates those tuning parameters. Other problems that people see?
You can't extrapolate.
Yeah, I have no idea what it's gonna do extrapolating. It'd be actually kind of fun to see what it would do, but we can do that next time on Thursday.
It's error distribution, I'm assuming, doesn't really track the data that well.
Yeah, so there's a couple ways that plays out. I don't remember what I plotted. I think this is plus and minus one standard error, and we can look. But there's also sort of these strings of positive and negative residuals. I mean, you want to check that formally somehow, but you can kind of see that like 2, 3, 4, 5, 6, 7, 8, 9, 10 positive residuals in a row there. Just looking at it, it doesn't look like, it looks like there's still some time series correlation in the residuals that the model's not dealing with. So it looks like if you fit it, you'd want to fit in another model on the residuals and then combine them or something, you get into some ugly process of trying to get rid of all of the structure in the residuals. So the true is shown in the black line, and I guess the red is just sort of wildly over smoothing, which is why you get this sort of pattern in the residuals, where some are positive and some are negative over time. Clumps of positive and negative over time. Yeah, I also don't like that there's no model to specify, so it's hard to interpret what the model is saying once you finish it. That sort of gets to John's point about how there's no hyperparameters. So there's not really any, once you fit the model, it's hard to make any inference. I don't know how to write up results from a Loess smoother except just put the plot in the paper and just say this is our predictions. And then this is a GAM fitted to the same data. So the GAM seems to do less, better than the Loess smoother to my mind. So at least it sort of picks up on this sort of decrease here. But again, has the same problem John talked about of, having hyperparameters, they're being tuned somehow and not easily interpreted. And then finally, the Kalman filter is just fitting the generative model. So if we generate data from this process and we fit the same the model to it, what are the guarantees that we have for maximum likelihood theory?
Should be consistent.
Yeah, so it should be consistent, and we should get good estimates of standard errors. So now we get into sort of consistency. There's sort of a wrinkle in our definitions of consistency with time series and spatial models. Maybe I can talk about right now. So has anybody heard about sort of different forms of consistency for time series models? I'll just start out saying it and it'll come up again later. But there's sort of two different ways. So what is consistency? I mean, what's our definition of consistency?
Doesn't really change through time.
What do you mean? Sorry.
Something is consistent if it doesn't change much through time.
Oh, well, okay. So yeah, that's like the plain English definition. Exactly. Yeah. So something that, but sorry, I mean like what do we mean by statistical consistency from the?
I think my understanding is that you just will hit the same parameters over and over to refit it, right?
Yeah. Well, right, and that's the tie to the plain English. I think I'm guessing is that like if you repeated the experiment, you would get similar things. So my claim from the first lecture was that, I think the definition of consistency is that as you increase the amount of data, you will converge on either the true model, or, the true parameters, or the optimal parameters. The problem with the time series model is there's a couple ways you could accumulate data. So in this model, you could either accumulate data by lengthening the time series that you have data for. So if you have data from time 1 to time 100, you could invoke consistency where you're increasing the length of your time series from 100 to 1,000 to 10,000 to 100,000. Or you could have consistency where you start having multiple measurements in every single time period. And so have people heard of terms for those two forms of consistency? Is that something that has come up for you guys before? So if you add more data within these are the terms that Andrew Gellin uses at least. If you add more data within your model period, he calls that infill asymptotics. And if you add more data, if you add more time periods with the same amount of data per time period, that's called sprawl asymptotics. And there's consistency guarantees that are specific to both of those types of asymptotics, because consistency is something about the asymptotic behavior of an estimator as you add more data. Why don't we wait? Maybe I haven't assigned homework 3 yet, so maybe I'll make it about those concepts and have a way to define it. Okay, so in this case, if we code up the Kalman filter, we've got to have, like Caitlin said, we've got to have the initial, we've got to have an initial state as a parameter. And then we've got the 3 parameters we talked about before. And we want to estimate those by maximizing the integral across this, the integral of the data given the random effects and given this hyperparameter, the measurement error, the variance of measurement error, and then this probability of the states themselves. And because this is first order Markov, we know that we can split this into a series of smaller integrals. And so in this case, we can, instead of this integral, we can split it into the probability of each datum given the state in that year, and the probability of each state given the state the year before. So because it's first order Markov, we only need to know that this probability is only, you know, in a given year, it's only dependent on the state the year before. So why is it useful to break, I mean, this is about, well, why is it useful to break this integral into a series of smaller integrals? So that's stuff we started talking about at the end of Thursday.
Is it the top one is like a T or NT dimensional problem, and the bottom one is just a two-dimensional, one-dimensional problem?
Well, exactly, yeah, so this one we've got, if we've got NT states, if we've got 100 states, this one's a 100-dimensional integral, which is crazy to think about. And I don't even bother with proper notation for it. Whereas this one is a series of two-dimensional integrals, and it's technically 99 two-dimensional integrals. So instead of this sort of mind-boggling integral, we've got a series of difficult but feasible integrals. So if we fit the Kalman filter, it ends up looking like this. And my claim is that by eye at least, this looks reasonable. So like, you know, there's a few places, well, most of the time, you know, the longest string of positive or negative residuals is maybe 2 or 3. Here, I guess we've got 1, 2, 3, 4, 5 positive residuals in a row, but there's not whole, you know, for the most part, the residuals don't come in strings. The true state is within this interval of the model. Okay, so that's all the theory I wanted to cover. So, so looking at the code, I'll just skip through how to fit the lowest smoother in the game. Let's see. Yeah, it looks like these. It looks like what I was doing. Well. Like here in the code, this is the one for the linear model. It looks like I was fitting negative 1.96 or 1.96 times the standard error of the fitted Y prediction value. So I was fitting a 95% confidence interval on the predicted unobserved state from a linear model. I'm assuming that standard error fit, this way of extracting it, I'm assuming it doesn't include the standard error of the observation process. So that's why I wasn't containing the observations at 95%, right? But down here we can see what we always do in TMB, which is, you know, load the library, we compile the CPP, the data is just, you know, the length is just the time series, and for convenience I put in the length of the time series is another data in. We've got the parameters include the fixed and the random effect starting values. We declare which one is random, and we make the object. And on the CPP side, I'm assuming people still want to be looking through. I mean, like I said, these weeks are supposed to be sort of consolidating things that we blitzed through in the first 2 weeks. So are people still, is this still useful for us to kind of go through the code line by line like this, or? Okay. So on the CPP side, there's, the data starts out by declaring all the stuff in our tagged list of data. The parameters start out with naming all of the stuff from our tagged list of parameters that contain the starting values. And in this case, everything is, let's see, so how can we do this? T apply, parameters, length. So, L apply. So if we look at the length of each element of our parameters, the first 4 parameters all are length 1, where they're scalars, whereas the last one is length 100, or it's a vector. And so each of these is declared as a parameter. This one's declared as a parameter vector. And then, like all random effects, all of the mixed effects models, we have a block of code that defines the probability of the random effects, and then we have a block of code that defines the data conditional on fixed and random effect values. And both of those log probabilities are aggregated into the joint negative log likelihood that we'll report at the bottom of the code. So our first state, log dt 0, which is the first because C++ number is the first element of a vector with index 0, is normally distributed around a parameter representing the expected. I mean, this is just one way to do this. This parameter log d0, and then we sweep through the rest of it, where the is anybody, so the pointer, I was going to use the pointer on the PowerPoint side. Does anybody know how to use a pointer in other, on a Windows machine, on other software?
I think you could just use the mouse.
Yeah.
You could see it.
So highlighting, people off-site, feel free to chime in if this is easier for you to see what I'm pointing at if I just highlight the code. Or maybe just tell me if the highlighting makes it harder. Okay, so this block of code from line 20 to 24 is the probability of the random effects. And because it's first order Markov, we know that the probability of the log density in time t is just a function of the probability in time t minus 1. I'm sorry, this is the lab code. I'm sorry. I was looking at the lab ahead of time.
That's good, because I was just trying to figure out where D0 was.
That's funny. Yeah, I'm sorry about that. The code for the lab is obviously pretty similar.
There it is.
Yeah. But the point, I guess, the inadvertent point is that it looks very similar here, where you've got a block of code for the probability of random effects, where alpha is just the drift term. It's sort of a, it's a directed random walk. So the expectation of x in time t plus 1 is equal to x in time t plus alpha. And why do we do this? Why do we put in log sigma p as a parameter and then we exponentiate it down here?
Because then you can have negative infinity to infinity as the sort of input.
Yeah, exactly. So we can estimate the parameters from negative infinity to infinity and make sure that the standard deviation down here is bounded from, well, to be positive real number. There's one other reason why we do that. Can anybody think of, maybe another reason? Well, there's maybe 2 other reasons to do that. Can anybody think of the other reasons why we use log of a standard deviation as a parameter?
It's closer to it.
What's that?
It's closer to a normal, so if you need to integrate it out, it's better with loss approximation.
Yeah, well, okay, so it's a fixed effect, so it's not going to be integrated out. But yeah, what from basic probability theory, does anybody know what the expected what is the, well, I don't know how to set this up well, but, so I won't phrase it rhetorically, but the variance, the sample variance of a normal distribution, if you sum across it, is chi-squared. And so a chi-squared distribution, you would think that, the estimate might be approximately chi-squared distributed too. And so in a lot of cases, you can approximate that standard deviation. You can get better confidence intervals for your estimate of a standard deviation if you do the confidence intervals in log space. So that's another benefit. And then the third benefit, I would say, is that the log ends up maintaining the scale of your parameters better. So you want, during minimization, you want all your parameters to be approximately on the same scale so that a change in 0.1 in one parameter causes about the same effect on the log likelihood as a change of 0.1 in another parameter. Otherwise, your minimizer will get kind of confused if parameters are on a really different scale. And if you do the standard deviation as a parameter instead of the log standard deviation, if your standard deviation gets to like 0.01, and then it goes from 0.01 to 0.009, that might have a big effect on your log likelihood. And so using the log standard deviation is a way of making sure that the effect of that parameter on the log likelihood is about constant regardless of its value. If any of those three made sense, that's sufficient to hopefully help you remember to treat the log standard deviation as a parameter, not the standard deviation itself. What does this true mean in this denorm?
Have it come out on the log scale.
Yeah, exactly. So it's just like an R, that true is saying that you want the log probability, not the probability. And the log probabilities are additive, which is how you can accumulate the joint negative log likelihood by, by adding, subtracting it across all your data. Okay, and then what does this stuff mean? What does report versus AD report mean?
AD report is what the standard deviation is, right? Whereas report's just the estimated parameter value.
Exactly. So you can always get. Were people using report versus AD report when doing their homework?
I use AD report for everything.
So
All the estimated things.
the one is, yeah. So AD report is helpful to get the standard errors on all this stuff. Is there any time you would want to use report besides AD? And is there any benefit to report outside of what AD report gives you?
Speed.
What's that?
Speed.
So one of them is speed. Another one that I want to get to is sort of just for debugging. So the benefit of report is you can get it at any point during estimation. So like AD report, you typically only make sense if you can run your model. Once you estimate your model, you can apply the delta method to get your standard errors. But report is something you can trigger any time just to see how your model is doing. So for instance, you could put in obj report and give it some other values for parameters. This might be too much of a tangent, so tell me if this gets boring. But I think it's useful for debugging. So obj, this is all of the parameters, the starting values of parameters in this case. And if I just run obj report on those starting parameters, I can output stuff that might be useful for me to diagnose what the model's doing. And then I can start changing those values and see what effect, I can use this to double check all of my code basically. So I can hand it any set of parameter values and then report out the derived quantities it's working with and use that to double check on the R side that it's doing what I think it's doing. So that's sort of a debugging hint, I guess.
That's better than using like print statement or something because you can manipulate it.
Yeah, I don't think that you can do print statements on the C++ side. Were you using them? Am I wrong, or?
I think I used report for something, but then like because you can report for data and parameters, any quantity.
Yeah, in theory, anything that's defined within TMB, you can report out and look at. I think. Okay, so that's, the point I'm trying to make over and over again is that, coding in TMB, coding a mixed effects model is very easy. So, really, there's a bunch of input stuff up here. The first 10, there's crazy gibberish first 4 lines. And then the next 10 lines are just input of parameters in the data. And really all you need in this model, the workhorse of this model is this block of, 7 lines of code that define the probability of the random effects and the probability of the data given the random effects. And, those, if you know your model, those are very straightforward to write. So I actually think that writing this up in TMB, once you're used to it, is not really any more complicated than, it's only 2 lines of code to do this for a GAM, whereas it's, essentially 7 lines of code on the C++, on the TMB side. But the benefit is you get a lot of extra power out of it, so.
How would you code this differently if you had multiple observations for each time step?
Yeah, so if you did that, what I would do is I'd put in, I'm just going to close this so that I can make sure that I'll just start typing and then it'll revert when I close it. The way I usually do that is I put in the data in long form. So instead of having, like sometimes people get in the habit of using ragged arrays, which I don't personally like doing. And so I'd rather have all of my data be in kind of long form data frame, and then I put in a new indicator variable t sub I or something. Let's just call it t sub I for now, which would be the time interval for every observation I, where sorry, that's not a parameter, that's data. And instead of y sub t, I would call this y sub I. So I've got some observations for every observation. We've got a value for every observation I. We've got a time interval for every observation I. And then on the C++ side, I would just put in everything. This line would be identical, 19 through 23 would be identical, but this line would be different, where it would, instead of the expectation of y sub I would be x of t, t of t sub I. Does that make sense?
Mm-hmm.
Maybe like I said, maybe this is inspiration for the homework, I don't know. But.
Can I ask about how, is this the same as the model you put up with the random effects or epsilon that were normally distributed around alpha in the slides?
Yeah, so the short answer is yes, this is a different parameterization of that same model.
Okay.
And thanks for kind of pivoting us back to what I want to make sure to cover before we end today, which is about separability again. So we've looked at the code. Somebody asked me about the 3 stages of debugging TMB. Anybody remember who I was talking about with that after class one of these days? Obviously, it left a very strong impression. Were people having debugging issues in TMB during the homework? I mean, I know some people were. So maybe I'll rephrase. What kind of issues did people have when debugging for the homework one?
Crashing R occasionally.
Okay. Okay, so crashing R is a
John told me
classic.
that's like overrunning a vector.
Yeah, so
Yeah. He did, actually, but a while ago. Yeah.
So there's three types of bugs in TMB. One of them is one of them on a Windows machine will crash R, and it's related to, well, maybe there's 4 types. One of them is related to, will crash R when you're using a Windows machine, and it's related to overrunning a vector.
Like your index is outside the length of the vector,
Exactly, yeah.
and it'll just kind of be like.
Then you'll get the bomb symbol in
Okay.
R.
Okay.
Yeah.
Thing restarts.
Exactly, in RStudio will, or
Yeah.
in some other stuff, it'll just crash your R.
Which could happen if you like start your index at 1 and instead of 0 or something.
Exactly. That's the classic sort of like looping from 1 to the length instead of starting at 0.
Yeah.
So that's one good bug. There's also, I'm sure people had a bug where they would program something and try to compile it, and the compiler wouldn't work, and you get some error message. When does that come up? If people nodded, indicating they had it.
Pretty much if you do anything wrong.
So those are,
Forgetting a semicolon.
Yeah.
Yeah.
Not defining a variable
Yeah.
properly.
yeah. So those are syntax errors, and those are, in my experience, I think those are the easiest to fix, because usually the compiler gives you a line number that tells you, I mean, it gives you a bunch of crazy gibberish, but if you scroll to the top of that, there'll be some statement about CBP : and then a line number. And you can always just go through, look for those line numbers and change that line of your CBP. So we've got syntax errors, we've got overrunning a vector. Did anybody have, well, I'll give you, we wouldn't have run into it yet. Another one is something where the inner optimizer says not positive definite. And that occurs when you've got a random effect that is not affecting the likelihood. And then the 4th type of bug I'll talk about is just where you build the model, it seems to be working, but then you simulation test it and it doesn't work. And in order of difficulty, I think the easiest is the syntax error, because the software tells you what's wrong. The next hardest is where you crash R, because you've got a good indication that there's a problem. The next hardest is the inner optimizer failing, because you have to do some stuff that we can talk about later. And then the hardest one is the model not working the way you expect it. And people publish models like that all the time, and then hopefully retract them later.
By which you mean like when you actually generate from your model, it's not the model that you thought you specified?
Exactly, yeah, right, and how would we, like, what, of the stuff we've talked about, how would we detect those sort of errors?
It happened to me in homework 1 when we specified the gamma distribution, but I misspecified it in my model, and so it got nowhere near the expected mean.
Exactly. So the easiest way to detect those logical errors, where you built your model, you wrote a model and it works. I mean, it runs, gives you estimates, it doesn't crash, but the estimates don't mean what you think they mean because you coded it wrong. The easiest way to detect those are, I think, just simulating. And that's why, people sometimes say that any model you build, you should simulate data from and do a simulation experiment just to make sure that you don't code it wrong. That's why, in Andre's lab, I think every single student, any model they do, will have to simulate data from that model and refit the model just as a check that you didn't code it wrong. Okay, so.
One of the things related to that I've also done is if you're testing your code and you have a dummy parameter in there, and you don't include the dummy parameter in your final objective function, then you can get estimates out of the model, but you can't get any of the standard deviations because something in the Hessian matrix will be 0.
Totally. Yeah, I skipped that. I guess that's the 5th type of bug, is where you have a fixed effect that's in your model that's not doing anything. And that means that the Hessian matrix of your fixed effects has, is reduced rank. So it's not invertible, so you can't get standard errors. And how would you check, any ideas about how you would check that case?
Run something with 80 report, and if you don't get a standard error. If it says NaN in the standard error, you know something's wrong.
Totally. Any guesses, I mean, knowing what we know, any theories about how you could check which parameter is causing the problem in that case? I mean, because the problem is oftentimes that if you do that, suddenly you can't invert the matrix, so you don't get standard errors for anything.
Can you just look at the Hessian?
Yeah, so the standard way to do that is to hand code getting the Hessian matrix and then do the eigen decomposition of that matrix. Somebody remind me if you want to see that. We can do it during lab. It's an exercise.
Did you end up figuring out how to get the Hessian matrix out?
Yeah, so that's what I wanted to show next here. So, this model, my claim is that this model runs really quickly. And, so that this Kalman filter for 100 time steps runs in 0.1 seconds, which is way faster than this would take in JAGS or other software. And the reason that it runs this quickly is because I've already coded it up in the parameterization that's separable. And we'll talk in week 5, we'll talk about parameterizations that are separable and not separable and how they give identical estimates, but one is the separable one's more efficient. For now, I just want to show what that means. So I'm loading package inla, which has the nice tools for showing this, and then I should have done this ahead of time. Yeah, okay. So you can extract the Hessian of the random effects using this function SPHess. And so this is what I was trying to find at the end of last class. If you run this, and SPHess stands for sparse Hess, and it's a function for extracting the representation of the Hessian matrix of random effects that TMB is working with. If you look at this Hessian matrix, it's 100 by 100, and that makes sense because we've got 100 random effects in this model. We've got, but it looks like, let's see, I'll just look at the top bit of this. So for people that stuck around, I found this eventually last class. So with people that were here, do people remember, does anybody remember what the dots mean here?
The structural zeros.
Yeah, so this is cases where this Hessian matrix of random effects, this is the partial covariance, or the Hessian, between random effect 1 and random effect 6. And that Hessian is guaranteed to be 0, regardless of any other values in this model. And so knowing what we know about the model, why is the first random effect and the sixth random effect, this Hessian guaranteed to be 0?
Because they're conditionally independent.
They're conditionally independent. There's this one-to-one mapping of conditional independence and the structure of the Hessian of the random effects. And that's sort of the punchline of this is why this class is possible, is that TMB automatically detects the sparseness of the Hessian matrix. So what does some of this stuff up here mean? The 6 by 6 sparse matrix of class DSC matrix. Any guesses what this means?
It's a 6 by 6 matrix.
Yeah.
It's
And
sparse. DSC matrix.
I have no idea what that is. Yeah, but and what does sparse mean in this case?
Has the dots.
Zeros.
Yeah, so it's, does anybody know, well, let's see, I'm not sure, not sure if I can trick this into showing how it's encoded. But a lot of sparse matrices are encoded internally using what's called a oh shoot, what's it called? Well, it's encoded internally as a matrix with 3 columns, where the first column is the row number and the second column is the column number. And the third column is the value for that row and column of the matrix. And that's a useful representation because out of this, this Hessian matrix is 100 by 100, or there's 10,000 potential elements that it would have to store in this matrix. But out of those, let's see, sorry about this. Out of those, only 298 of those elements of the Hessian matrix are non-zero, and the rest of them are guaranteed to be zero structurally because of this structure that this first order Markov state space model has. Does anybody want to? So that's sort of the second explanation I'm going to give about sparseness today, is that it has something to do with the structure of the random effects that TMB is able to detect automatically.
You can see that if you just look at the structure of Hess, it'll show that.
Oh yeah, you mean like just look at this diagonal part where it's.
No, if you just do like STR of Hess,
Oh, okay.
it'll show you the like slots where it's storing like the X values and then.
Got it. Yeah, and there's some way that you can access this. That's cool. What's in there? I don't ever use that str function. Well, I have no idea what. But so it's being stored internally with 7 slots. Well, that's cool. I'll look at that later. Yeah, what else did I want to say about that?
Plus there may be some non-structural.
There's one other thing that I'd say about this, which is that this is called a tri-diagonal matrix. So this matrix, oh yeah, that's what I wanted to do. You can also just look at the whole thing using the INLA. So image in INLA shows a plot that looks like this, where it's white anywhere that's guaranteed to be 0, and then it's a positive number on the diagonal, and it's a negative number on the off diagonal, where it's, it's like negative 0.1. And so this image function is a nice way to depict the Hessian matrix. We'll get into models where that ends up looking a lot more complicated. But in this case, this is a tri-diagonal matrix, and that should kind of make intuitive sense because it's only non-zero on the diagonal, and specifically on 3 elements, or the diagonal plus the element before and after it. It's tri-diagonal, but we were only using 2-dimensional integrals. Is there any thought about why it's tri-diagonal, but there were these sort of 2-dimensional integrals, or is it dependent on the one before it?
Because I don't know how to say this well, but like basically it's only using like the bottom half of the matrix and the upper half, where it's like the non-zeros on the upper half are pretty much just repeated values from the lower half.
Yeah, right. Well, so that's one way to, we know that this is, this matrix will be symmetric, and it arises, as I hear you saying, it arises because we've got a correlation between time t and t plus 1, because that arose when we looked at the dependence of time t plus 1 on time t. So even though we're coding up the model where time t plus 1 is dependent on t, where time t is dependent on t minus 1, it automatically works out that a given state is correlated with the state before it and the state after it by sweeping through it. I don't think I explained it any better than you did. It's hard to explain, but yeah. Okay, so that was the material I wanted to get through today. Are there any questions, or if not, I'll talk about REML, which I was going to cover last time.
Shouldn't the sum of, since it's a 100 by 100 matrix, shouldn't the sum of Hess, which equals 0, plus the sum of Hess, which doesn't equal 0, equal 10,000?
Yeah, so it's super weird. I should have looked this up beforehand, because the way it's stored internally does some weird stuff in terms of these large bold statements.
Okay.
So you would, what I take it you're saying is, why is it that the sum of Hess equals 0 plus the sum of Hess not equal 0, why does that not equal 10,000?
Yeah.
And I don't know.
Would be just a diagonal, right? It's 100
Yeah.
entries. It's
Well,
just a diagonal.
Yeah, but I don't know, I think it has something to do with the way it's being stored internally. I have no idea. And I wish I'd remembered and just shown the second line so we could ignore this problem.
What happens if you change it from like a DSC matrix to just like sum of as matrix Hess equals?
Totally. So that's a good check. And later we'll see what effect that has. As matrix. So if you can coerce it to if you use as matrix and then look at the structure of as matrix, it's just instead of being a sparse matrix now, it's just coerced to be a normal matrix. And if you look at the first 6 of those lines, now it's filled in zeros, so it lost all of this sparseness. And if you plot it, because it's not a sparse matrix, it now uses a different image function. So you can always coerce a sparse matrix out of being sparse. And then there's also, you can cast it from a dense matrix back to a sparse using, I think, a function called an as in R that I would have to look up to figure out how to do it. And again, we'll get more into that, I think, in week 5. Any other questions for now?
You said you'll go over how this parameterization works later in the course.
Yeah, or like the comparing a separable parameterization where the Hessian is sparse versus a non-separable parameterization that will give you the same MLE, but where the Hessian is not sparse, and therefore it takes a lot longer to run. That's what we'll look at in week 5. Okay. If there's not any objections, I'll go back to REML for a moment. First of all, what do people know about REML? Just from hearing about it.
Restricted maximum likelihood.
Yeah, so it stands for restricted maximum likelihood. It was already up there, but what's the benefit of restricted maximum likelihood? Well, let's take a step back. So we talked about we talked about how a maximum likelihood estimate is guaranteed to be consistent in the sense that if you accumulate data asymptotically, your parameter estimates will converge on the true value if the model is correctly specified, or the best value if it's not correctly specified. We didn't say anything about bias. So there's no guarantee that maximum likelihood is guaranteed. It'll be unbiased in the sense that the expectation for a finite sample size might be different than the true value. And is there any case that people can think of where maximum likelihood often gives a bias? There's sort of one. There's a couple of kind of textbook examples of bias in maximum likelihood estimators.
Variance.
Yeah, the main textbook one is the variance. So if you look at the maximum likelihood estimate of a variance in a linear model, then the variance estimate for the maximum likelihood estimate, the maximum likelihood estimate of that variance will just be the average difference squared between your model fit and the data. And that's what, my understanding is this is actually that's sort of what made Pearson, Fisher and Pearson have a falling out originally, is that Pearson presented this as the best estimator for the variance of a linear model, and Fisher came along and is like, oh, you're missing a -1. And so,
Friendship over.
yeah. And so, the point is that, I mean, sometimes we call this a degrees of freedom correction, or there's actually a term for it that I tried to memorize once to sound really silly, but I can't think of right now. And the point is that, you know, this mean is being estimated, and so it's sort of systematically shrunk towards the mean of the data and away from the true value. And so these deviations will always be slightly less than what they should be, you know, if you were using the true value of the mean. And so this sort of increases your variance slightly to deal with that degree of freedom. That's sort of the intuition I think you get if you do this, you know, in an intrastats class, like where that negative one comes from. The issue is that the same problem arises for random effect estimates. So if you've got a linear mixed model where you've got a measurement variance and a variance of the random effect, those variances of the random effect also have that same bias, where they're biased slightly low. And so REML originally was a way of dealing with that bias kind of analytically in a linear mixed model. You can work out what that bias is, and it's kind of like the -1. But it's not clear how to do that in more complicated mixed effects models. And so the key to REML is that you can always do something like REML in a mixed effects model by integrating across the non-variance fixed effects. So looking at that in our code, well, let's see. Let's look at it in the model first. So these are the four parameters we're estimating in the code. So which of these are variance parameters?
So let's do.
Yeah, these two. So the non-variance fixed effects are these two. And you can get REML estimation by just integrating across those parameters as well. And that's what I've sort of had in the code a bunch of these lectures. So if you turn on REML, well, we're out of time, but I'll just show this really quickly. If you say use REML equals true, all that's doing in the code is it's saying that down here, it's telling my function that I want to treat not just x of t as random, but also these non-variance fixed effects as random. So now suddenly I'm treating more of the parameters as random effects. And if I compile the object, those fixed effects are no longer showing up in, you know, those, I'm still going to call them fixed effects because that's what they are in terms of inference, but I'm treating those fixed effects as if they're random with a flat prior. And then you just proceed with estimation as you did before. And these estimates of variance parameters are, by theory of REML estimation, they're guaranteed to be, well, slightly less biased. I mean, I think they're guaranteed to be unbiased, actually, in the Kalman filter case. So that's the 30,000 foot explanation of what REML is and why it's been showing up in the code. Any questions about that? Or, I mean, we're out of time, so feel free to leave or ask questions if you want. Okay, well, thanks everyone. Yeah, and Dan said that Dan said online that you can use cout, std : cout on the C++ side if you want to print something discrete, which I don't understand.
Although it boosts it 4 times.
What's that?
If you do that, it shoots it out 4 times.
Every time? Okay, that's funny.
Environment.
Cool. Okay, thanks everyone.